Hey, this is chapter 12 of Exponentials. It's our last chapter for this year, and let's just go crush it. Uh, exponential functions. Oh, yeah. We've learned about a variety of polynomials. A polynomial, PS, is any equation where the powers are whole numbers. So we've seen constant equations like y equals 3, which graphs like this. We've seen linear equations like y equals 3x plus 4, which graphs like this. We've seen quadratic equations like y equals x squared, which graphs like this. And we've done inequalities like 2x plus 3y is less than 12, which would graph kind of like this. Those are all polynomials because if they have any powers, they're whole numbers, like 1 or 2. An exponential is a completely different type of equation. An exponential is an equation where the power is a variable. The variable is as a power, not as a multiplier of some sort. So we're going to talk about what happens as you try to graph or work with or look at y equals 2 to the x or 3 to the x or 1/2 to the x. We're also going to just really briefly learn about a whole new number, like a number that's not expressed with digits, and talk about compound interest. So should be good. Okay, I'm going to graph y equals 2 to the x. A couple things I want you to keep in mind before we do this. Remember that a negative power flips a fraction over. Okay, that's really important you remember that. A negative power does not make something negative. Okay, it's not this. A negative power flips a fraction over. So I'm going to plug in numbers for x that I think are going to be kind of easy to calculate. So we'll label this table x and y. In the middle of this table, I'm going to put a 0. 2 to the 0, if I'm plugging in 0 for x, is 1. So let me just draw an x and y axis on here real quick. I'm going to make it like this. You'll see why I made it like this in a second. I plugged in 0 for x. I got out 1 for y. That is the y-intercept. 0, 1. If we plug in 1 for x, obviously 2 to the first is just 2. If we plug in 2 for x, 2 to the second is 4. If we plug in 3 for x, 2 to the third is 8. Now we're almost getting so big that I can't graph anymore. 2 to the fourth is 16, and 2 to the fifth is 32. 16 I can like pretend like I can fit on here. Let's just say this is the point 4, 16. But then it goes to 32 and 64 and 128 and 256 and 512 and 1024 and 2048, and it just keeps doubling over and over and over and over and over. This grows incredibly fast. Insanely fast, really. This is called exponential growth. Exponential growth is whenever you have a repeated multiplication by some base. Okay, so in this case, the base, which we're going to call b, the base value is 2. Let's talk about negative values. If I plug in negative 1 for x, 2 to the negative 1 is a half. 2 to the negative 2 is a quarter. And 2 to the negative 3 is an eighth. You'll notice these are all just reciprocals of each other. Well, here's a half. I'm going to call that a quarter, even though I can't graph a quarter super well. Here's an eighth. Next would be a 16th, and a 32nd, and a 64th, and a 128th, and a 256th. And something really important happens here. This graph never touches 0. The fractions keep getting smaller and smaller and smaller. The fractions keep decreasing. But they're always going to have something there. Like 1 over 2048 is something that isn't 0. 1 over 4096, the next value, is something that isn't 0. This graph will never, ever touch 0. And so this right here has what's called an asymptote. yes, that sounds kind of funny. I'm going to write it in pink to make sure you see that it's different. Asymptote. Don't pronounce that P. Asymptote. An asymptote is a line that your graph continually approaches but never touches. See, I don't have to say never touches because continually approaches implies you never touch it. If you touched it, you couldn't be continually approaching it. This asymptote is the line y equals 0. Every exponential graph has an asymptote. A line that your graph gets closer and closer and closer to but never touches. This is called exponential growth because it's growing. It's nice when we name things simply like that. You'll note this has no roots. It has no roots because it doesn't touch the x-axis. Okay, let's do another example. This is going to be very similar, but different. I'm again going to plug in numbers from -3 to 3. And I'll start with 0. 1/2 to the 0 is still just 1. 1/2 to the first is a half. 1/2 to the second is a quarter. And 1/2 to the third is an eighth. 1/2 times 1/2 times 1/2 is an eighth. An eighth is 0.125. A half to the -1. Half to the -1 is 2. A half to the -2 is the same as 2 to the +2, which is 4. And a half to the -3 is the same as 2 to the third, which is 8. Whip up a real quick. I'm going to live with that line. Live with that line too. No, my second line's way better than my first line. I wanted this tool. I have the point -3, 8, -2, 4, -1, 2, 0, 1, 1/2, 2, 4, 3 and 8, 4 1/4, 16th, 32nd, 64th. This has exponential decay. It has exponential decay because the graph is going closer to the asymptote as it goes to the right. You could think, as we zoom to the right, this is getting smaller and smaller and smaller. The asymptote here is y equals 0. So this is basically the exact same graph as the last one, only these values were flipped because the base was flipped. The base was 2, but it became a half. So all these things switched around also. So our previous graph looked like this. Well, more like this. You get the idea. So that's how you can graph exponentials. Identify first if they're going to be growth or decay. If the base is less than 1, it decays. If the base is greater than 1, it grows. But if you identify that, plug in points and graph, you should be fine. There is one last little piece you want to worry about, however, and that's where the asymptote is. So I'm going to create real quick one other equation for us to graph. We are going to graph the equation y equals, I can write, don't worry. Y equals 2 times 3 to the x plus minus 2, minus 4. 2 times 3 to the x minus 4. Okay, the game's not going to change. Plug in these numbers for x. So right now, exponentials have this equation, y equals a times b to the x plus k. If we have something being added or subtracted out here, we call it k. So right now my a value is 2, my b value is 3, my k value is -4. Because the base is greater than 1, this is going to have growth. The graph's going to do something kind of like this. But let's plug in points and calculate. I'm going to do this in my calculator just to show you that it can be done in your calculator and can be done pretty quickly. If I plug in 0 for x, that's 2 times 3 to the little up caret is 0, 2 times 3 to the 0 minus 4. That's me plugging in 0. 2 times 3 to the first minus 4. That's me plugging in 1. 2 times 3 to the second minus 4. That's me plugging in 2. And I'll do one more. 2 times 3 to the third minus 4. So I got the values of -2, 2, 14, and 50. Let me do the negatives. 2 times 3 to the -1 minus 4 is -3.3. Two times 3 to the -2 minus 4 is -3.7. And this next one's going to be -3 point something very small. 2 times 3 to the -3 minus 4. -3.925. So if I plotted these points, I'm going to make an x-axis here, or y-axis here, and an x-axis here. So I want to try to give myself space on both sides, space to go above and below. I have the points 0, -2, 1, 2, 2, 14 is like, okay, way up here. I have -1, -3.3, which is like here. -2, -3.7, which is like here. And -3, -3.97, which is like here. This graph is going like this. Now, I don't like that I haven't labeled this. I don't think I labeled my last graphs either. You have to make sure you do that. I'm trying to save some time, but I shouldn't do that. I should actually just label these. Makes them much easier to read. This asymptote is at -4. The k value is your asymptote. Always. Your asymptote will always be at y equals k, whatever k is. Since k was -4, it's my asymptote. Okay, so you can graph any exponential function, plug in the numbers -3 to 3, plot them, figure out if it's growth or decay, and find your asymptote. I want to real quick talk about evaluating. I just showed how to do this, right? Like all three of these you can just do by typing them into your calculator. 5 times 1/2 to the -4 plus 8. 88. So this would come out to 88. But I want to talk about this. E is a number. Kind of like how pi is a number. Pi is a Greek letter. Like in the Greek alphabet, one of the letters is called pi, like how one of our letters is called T. E is also a number. 2.1828. You can find E on your calculator. If your calculator is like mine, if you press second ln. ln is this button right here. See where that line's kind of pointing? ln is right here below log. If you do second ln, that gives you e to the. E to the third is 20.08. E to the 10th is 22.026. And just because I haven't really made this super clear, just plain old E is 2.718281828 blah blah blah. I actually forgot the 7 here. 2.718. E is a number that represents 2.718, and it goes on and on forever like pi does. I'm not going to explain right now what it is, okay, like where it comes from, why it's useful, but know that it's extremely useful and extremely important and comes up all the time. I got to the point when I was a math major where if I didn't know the answer to something, I would frequently guess E, and it was often kind of on the right track. 2 times e to the 4th minus 1 is 108.2. So that's how you calculate with E. And that's all we're going to do with it for this lesson. Okay, last thing, compound interest. Compound interest is how money grows in accounts and investments. Not the only way, but one way. It's a very useful way. It's got this formula that looks like a big mess, but it's fairly straightforward. You just plug in numbers and calculate. A represents your final amount. P is your principal, which is your starting amount. R is your interest rate, written as a decimal. N is the number of times you compound in a year. That's typically going to be 12, but not always. N is going to be the thing you find the most confusing, so we'll talk about it the most. T is time in years. So all we're going to be doing is plugging numbers into this formula to calculate the value of A. We're always going to be trying to find A. So here, an investment pays 6.2% annual interest compounded monthly. All the word compounded means is just when do they calculate your interest. They're going to take 6.2% interest and give it to you once a month, which means they're taking that 6.2% and they're breaking it into 12 pieces. They're dividing it by 12. That's what this right here is doing. It's taking the 6.2 and dividing it by 12. So if we invest $5,000, how much do we have in 8 years? Well, this 6.2% is our R, our rate. Move the decimal 2 to the left, 0.062. Since the appointment is, or the interest is being compounded monthly, our N value is 12. Our starting principal P is 5,000. And our time T is 8. I'm going to plug all of those numbers into this formula. Let's put this in green just so that I can be consistent with colors. So the formula is going to be 5,000 times, this is A equals, times the number 1 plus the fraction of 0.062 divided by 12, all to the power of 12 times 8. I plugged everything into this formula. We're trying to calculate A. Now I just type this into my calculator. When you type this into your formula, so I'm going to type in this equation right here. When you type it into your calculator, you want to be very particular with your parentheses. I'm going to do 5,000 parenthesis 1 plus 0.062 divided by 12 close parenthesis to the, and then this to the also has to be in parentheses, 12 times 8. We want it to be doing to the 96, not to the 12, and then whatever that number is, times 8. We want the to the to all be done together at once. Press enter. You would have $8,200.22. So you'd make $3,200 for not doing anything, which is pretty sweet. It's nice how compound interest works that way. That was 8 years, so making, $3,200 in 8 years isn't like super fast. But, again, you're not doing anything. It's just growing for you. Okay, now I said the toughest thing about this is going to be the value of n. I want to show you this can change. Suppose, instead of this being compounded monthly, let's say it was compounded quarterly or semi-annually or something. I'll go with quarterly. Quarterly means 4 times per year. Had this said quarterly, we would have changed our n value, instead of being 12, to 4, because that's 4 times per year. So I would jump over here and change this from a 12 to a 4, and change this from a 12 to a 4, and run the calculation again. You're going to see it doesn't change all that much. I press second enter to pull up my previous equation. Wherever I see a 12, I'm going to delete and change to a 4. It's almost the same. We're $21 shorter than we were before. Had it said semi-annually, the end value would be 2. Had it said daily, the end value would be 365. So the end value is just how many times does that thing occur in a year? Because there's 12 months in a year, n equals 12. Because there's 4 quarters in a year, n equals 4. That's the idea. All right, we did it. An exponential function has a variable as a power. It's often written in the form y equals a times b to the x, or y equals a times b to the x plus k. Although I don't actually think you see any k on your homework. If the b value is greater than 1, you have growth. If the b value is less than 1, you have decay. The asymptote is the line your graph approaches but doesn't touch. And exponentials can show compound interest. Next time. Later.